commence in 30 seconds. Warning. ICAN laser ignition will commence in 20 seconds. Warning. ICAN laser ignition will commence in 10 seconds.
And so ICAN's search for what lies beyond the Higgs boson begins. The most powerful laser ever conceived is switched on. This scenario belongs in the future, yet the research required to try and make it happen has already started. ICAN is an international consortium initiated and coordinated by the École Polytechnique in France. The other principal partners are the Optoelectronics Research Center in the United Kingdom, the Fraunhofer Institute in Germany, and CERN in Switzerland. But exactly what is the idea?
ICAN is an international project to try and develop a laser which is a combination of many fibre lasers into one in order to provide us with the advantages of short pulse lasers, but also the advantages of high average power that you can get from fibre lasers.
Very high-powered lasers have been tested as possible particle accelerators, but with mixed success. Although the laser pulse they can produce is massive, having fired once, the machine has to stop before it can do the same thing again. This is called the repetition rate.
Now, existing huge laser experiments fire sometimes only 4 times a day. We're now talking about the possibility that you could do this with an average power so that it's on all the time.
The reason this is possible is because of the unique way the laser is conceived.
What happens is you start with a single seed laser and then you split that into 8 different channels, amplify, split those channels into 8 and then split those channels into 8 until you get up to, say, 512 amplifiers. And then those 512 amplifiers, the beams have to be synchronized and brought together to make a single beam. In practice, what we're trying to do is build on the fact that within telecommunications you have a lot of components which have already been developed. And so the idea of making, say, 10,000 lasers for a single project is much easier because the infrastructure is already there.
We know with short pulse laser we can really produce already gradients, very high gradients, maybe 1,000, 10,000 times higher than what's possible with conventional technology.
Here at the Fraunhofer Institute in Jena, Germany, the first working ICAN fiber laser model is being put together by a team of engineers from different disciplines to test the concept.
ICAN is a consortium which serves as a platform to bring people from different areas together. People from accelerator physics, people from laser physics, but also people coming from optical system design. We have found the idea to develop novel sources, light sources, which directly address the needs of this accelerator people. And Gérard Moreau, in fact, he picked up this approach and came up with a very impressive idea, in fact, a unique idea. He came out with the idea to develop a fiber laser system which is based on several hundred thousands of lasers which should be combined. Well, we have demonstrated that it is possible to combine 4 up to 8 fibers to 1 gigapulse, and of course the control of the phase of each of these individual fibers is a main technological challenge.
The main amplification stage consists of 4 different amplifiers. They are coherently combined. So actually what happens is the light starts here, and here are polarization splitter cubes, and these cubes just splitting the light into beams. Actually here one beam is passing through and the other beam is reflected here. Then here's the second cube, this does the same again. And there's a third cube doing also the same again. And so we end up from 1 beam to 2 beams to 4 beams, and each beam is seeding an amplifier. Then each amplifier amplifies the light to some several hundred watt level. And at the end we recombine them again, and here we don't use cubes, we don't use special mirrors, and here we have also again 3 mirrors returning in 1 intense beam, and at the end we send this 1 intense beam into the compressor, the box with the grating again, compress it in time, and have a powerful, high average power, high peak power laser at the end.
The fiber laser brings for the first time the idea that you could take 1 million of these and combine them together to achieve what no other laser can do. So you have an additional parameter of using millions of lasers together to achieve a new form of laser. And this has made all the difference to the idea of wake field acceleration for the next generation of certain accelerators, for example.
As a particle accelerator, ICAN relies on something called wake field acceleration.
So wake is the word coming from conventional ship. Water is sucked in, so there's a depression of the water. So that depression of water will cause the ripple effect behind the boat. That's called the wake. Now, a similar thing could happen if instead of a boat, I put the laser pulse. And the laser pulse now is racing instead of the surface of the lake. Now I put the plasma. Plasma is now pushed by the laser pulse forward, and behind the laser pulse, plasma electron is sucked in, and therefore depression of the density of electrons. That causes, just like a wake of the surface of the lake, now we are making plasma waves behind the laser pulse. And the wave is also moving at the speed of light. Everything is moving at the speed of light. So the waves are moving what we call relativistic speed, and very, very nice waves. So that's the laser wake field, and that's what we take advantage of.
What is very interesting about these wake field accelerations, the limit right now of conventional accelerators is the breakdown of material.
And so the intention with ICAN is to then use that technique, but use it at very high repetition rate, and chain those amplifiers together to make a particle accelerator that's at very high electron energies.
The Higgs field is a theory which explains the creation of the mass for the different particles and so forth, for everything in nature basically, but not seen yet. And what happened some months ago is that here at CERN, in the collisions of LHC, we found evidence for such a particle. In the case of these laser-driven systems, you will need either a high-power laser or a combination of many low-power lasers, fiber lasers, like in the case of ICAN. You combine their power and then you put this light energy, the laser energy, into the plasma, into this gas, creating the plasma wake fields. And again, there is an electrical field vector speeding, accelerating the particles. These high-power lasers can deliver pulses of enormous energy, but not very often. So the ICAN, with this low laser power approach, but combining thousands of them, tries to overcome this problem. And if they manage with ICAN to show repetition rates and beam qualities which are in several hertz ranges, then this is already very, very promising. It seems to be scalable, and the advantage is indeed that the very first step is to work and optimize low power systems. Still, when we talk about terawatts, high powers, and the step between the low power part and then combining them to the high power part is the challenge that needs a proof of principle. That means, my personal point of view is, it needs a test facility.
This Higgs discovery it's a phenomenal discovery. What people have done at CERN is absolutely incredible. It's the fact that now we found it. Okay. And so we have really to look at what's beyond it, because certainly there is something else beyond it.
What is beyond the Higgs boson remains unknown, but each new discovery takes us closer to the greatest mystery of all. What happened in the beginning?